So, a couple of people have said, hey, can we talk about the numeracy questions after? Absolutely. One of the things that we're going to do, though, is you saw in the readings that the first half of the readings was like, let's, try and get familiar with functions, because we really didn't use functions a lot in the first half of the year, right? Like when we did financial math, functions didn't really come into that a lot. Linear algebra function, not really. And same thing with, there's a little bit in the probability section, but not a crazy amount. But integral and differential calculus, like we're about to be doing for the rest of the year, is all about functions, right? Calculus is the study of functions. So we want to make sure that, we're kind of comfortable with the basics there. And I think a lot of people, I think you learn about functions in grade 10. I think like that's the place where you learn about it, right? And so you've probably adopted and ingrained certain ideas about functions. Some of them aren't great, and we'll try and fix that as the case might be. Inverses is a big one that we know students have trouble with, so we're going to try and work on that. So let's start doing the poll questions, and then let me take a look at these questions in the chat there, but let's start with the poll questions first. Let's go straight to this one, which really looks like a numeracy question. We'll do this, and then I just need to fix my screen. And there we go. Right, yeah, very similar to A7. Yeah, okay, so, right, this thought that you're doing it all wrong. So one of the things that I really recommend, and obviously this is such a pain in the ass to do online. I really do get that. I mean, it's hard to make connections when you're in person, let alone online. But a big thing to do, and I know that there's a lot of fear when you're doing math, like what if I'm doing everything wrong, right? It's easy to think that you're doing something correct, but you don't have anything to check off of. And I think that's why so many of you enjoy having solutions, right? Because you can then check your answers, and if you got a right answer, you probably did it correctly. A really critical and important thing to do, though, is to, if you have a small group of friends or a relatively small study group, is to work on questions together. And even if you're not actively working on it together, if you're in a group chat, in the Discord, on Piazza, whatever the case might be, you can post your solution and be like, hey, everyone, this is how I did this question. Do you agree? Did you get the same answer? And get that feedback from your peers as well, right? So obviously you can use instructors and TAs for feedback on your work, and we're happy to do that. And if you ask anyone who posts this stuff on Piazza, there's lots of people who work on their exercise problems on Piazza and then post their solutions to Piazza and say, hey, listen, do you have any feedback for me? So some people do that. And, but yeah, I know there are group chats out there, and be careful though when you use group chats, right, for the obvious reason. But, so people will do that and will throw their answers up and say, hey, listen, did everyone else get the same answer? What do you guys think? And, people will give you feedback. And yeah, I mean, that's a great way of being able to help and figure out and see, if you did your question correctly. So I got a private message saying, are you referring to the, the end of chapter questions only? Or the poll questions, or like, what are you talking about? The answer is everything, right? I mean, except test questions, right? Don't do that for test questions. But yeah, I mean, like you can do that for absolutely everything. It doesn't matter what it is, whether it's the poll questions that we do in class, whether it's the end of chapter exercises. You're right. Maybe don't do that for assignments. There's things you can do with assignments, but you have to be careful, right? Because you don't want an academic offense. No, it means the inverse. So I got a direct message saying, what does the -1 mean? In the F, it means the inverse function. Okay. So for assignments, what you should do, and again, I very much encourage you to work together. Okay. I don't want you to do math by yourself. And I've really said that, strongly since the beginning of the year. Don't do math by yourself. For assignments, though, what you should do is you could get together with a group of people, and if you have a whiteboard, or if you're in person, find a blackboard or a room with a blackboard, work out the question together. But what you should do then is once you as a group have figured it out, go away and write up your solution on your own. Okay, and this is the important thing, because when you go and when you write the solution on your own, like don't take pictures of the board or anything, because if you take pictures of the board, you'll be tempted to copy that down. And when you copy that down, if everyone copies down the same thing, that's going to be an academic offense, because even though you might have collaboratively written that, it's no longer your words, it's everyone's words. And your assignment has to be your words, not half your words, half somebody else's, right? You can't do that. So what you want to do is you work together, you solve the problem, you internalize how the solution was done, and then when you go, you write the assignment solution by yourself using the ideas that you and your friends discussed and figured out the solution. And in doing so, your answer is in your words and your words only, right? And this makes sure that there shouldn't be any chance of an academic offense, because the reality is if I took any 5 of you and even showed you a solution and then put you in 5 different rooms and said, try and write down that solution exactly the way you saw it, you'd all write down something different. And that's not even what I'm asking you to do, right? You kind of solved it loosely yourselves with a group of friends, and then you went to different rooms and wrote up your solutions. That's how you avoid an academic offense for assignments. Yeah, and so, yeah, there's a direct message here saying, I think students get overly confused when it comes to group chats and not committing academic offenses. It is tough, right? There is even not when it's group chats, even just when you're working in person, there is a fine line there between collaborating and excessively collaborating, right? And that's why it's so important that you go somewhere else and you write the solutions yourself. Because if sometimes you'll get into those study groups and there's just a mooch, like somebody who isn't contributing to the conversation and is just looking to try and get the answer. If you don't let that person write anything down and then they have to go somewhere else and write down the solution in their own words, they're not going to be able to do it, right? Because they didn't contribute to the solution. But if there's a bunch of you and you're all contributing to the solutions and you really understand it, then you should be able to go away and write your own solution down, right? Like if you contributed to the study group and really understand what the solution is, you shouldn't need to take pictures of the board. You can go away for 5-10 minutes, write down your solution and come back and work with everyone, right? And that's just, maybe it sounds like a little bit of a pain, but that's for sure how you avoid kind of an academic offense, right? Group chats are a big, scary thing. I recommend, I really do, for term tests, if you have the ability to easily leave a group chat and come back in, I suggest that you do it. Because the reality is if somebody posts a solution into the group chat, if you're part of the group chat, you can be thrown under the bus for an academic offense, whether you looked at it or not. You're just part of the group chat, and some jerk in the group chat posted a solution, you're potentially in trouble for an academic offense. Now, I don't think that I personally would ever pursue any of you for that, for just being in the room at the wrong place at the wrong time. But that being said, obviously we would take a much closer look at your work if we knew you were in the group chat when that solution went up. So just, if you have the ability to leave during the term test and that way we know you weren't in the group chat, and then come back when the term test is done, that way you can be safe, right? It's really not worth an academic offense. It sucks. First one is usually not too bad, but especially when you're getting into second and third, you're in a lot of trouble.
It's also really easy to become biased when you look at something. Like when someone sends work, even if you not mean to copy it or you weren't even mean to look at it, sometimes you look at someone's work and then you naturally start thinking the same way they thought, and you somehow model your own solution, but it looks very identical to that solution that you saw earlier, which causes two things. If that solution was wrong to begin with, now you have a wrong answer, which is horrible. And even if that solution was correct, by copying it, sometimes copying it a little bit too verbatim, you're easily going to get caught for because we look at solutions very in depth, and when we have solutions that are similar, we flag them, and it's just a whole ordeal after that. So it's not worth it in the long run.
Mm-hmm. Yeah, so just be careful about that. Okay, cool. So let's see. We're a little spread out. It seems like not many people had a great idea about what to do. But believe it or not, not the overwhelming majority, but the majority of people did get this correct. Okay, so majority of people or plurality of people said B. B is absolutely the correct answer. Okay, so obviously one of the big things that we talk about, and this is obviously related to the assignment as well. So, this is going to be, I shared the wrong thing. So I'm gonna have to unshare this and just reshare it. Give me a second here. So I think we need to have a talk about inverses, right? Because I think inverses, just even based off of Piazza and everything, people are having a lot of trouble with this. And that's okay. We knew it was going to happen, right? That's why specifically we asked these questions. Okay, so let's do this. All right, now does anyone know what an inverse is? Let's before we even start that, what is an inverse? Can anyone tell me? What does an inverse do? Okay, all right, so it reflects the functions. We switch x and y and solve for y. It undoes a function. Okay, so there's a couple of things here. The inverse of a function, inverse of a matrix. Oh, that's a great question, Stanley. They're actually really, really related. Okay, yeah, so there are a couple of things here. So I know that for many of you, the way that you've internalized what a function is you say you switch x and y and you solve for y or whatever the case might be, right? So that's how you actually compute the inverse of a function. But if you try and do that here, we run into a lot of trouble, right? Like if we were to try and do that with this thing, right? So if I wrote this as like x is equal to y cubed plus y plus 1, and then solve for y, we'd have a lot of trouble, right? Like we wouldn't be able to do that. Solve for y, and I'm going to put, triple question mark here because how would you do that, right? And actually, in particular for this question, this function is chosen specifically to make it very, very hard to actually solve this for y. So that's how you would find an inverse if it's possible. However, there are lots of functions that have inverses and you can't write their inverses down. Believe it or not, there are lots of functions that exist, but you can't write down what they are. Okay, so I want to be a little bit careful about this idea of this is what the inverse is. You switch x and y. That's actually not what's happening. Now, a couple of you have said undoes a function. That's a great answer if we understand what undoes mean. Okay. Now, I know that many of you, when you think about a function, what is a function? Actually, can somebody, maybe this is a better question. What is a function? Like, what does it do? What is a function? All right, it seems like such a simple, okay, yeah, absolutely. Oh, these are great answers. Okay, so it takes an input and it produces an output, right? I think many of you, and yeah, absolutely beautiful. So many of you, I think when you think about functions, you think about graphs. Is that fair? Like I think if I said f of x equals x squared, the first thing that pops in your head is like a parabola, right? That's how you think about it. Okay. So that's okay. That's gonna be really, really troublesome when we get to like multivariable stuff. But that helps you visualize. That is an assistive aid only, right? That's not what a function is. A function takes an input and produces an output. That's the important point, okay? So let's say recall a function takes an input to an output, right? So if I say something like, here's my function, f of x equals x squared, what that means is if I provided an input, the function manipulates that input and then spits out a number, right? And in this case, it spits out the number 16. And when I write f of x is equal to x squared, what I'm doing is I'm telling you what the formula for that function is. That being said, you can still have functions where you don't know how the function works. You just give it a number and it gives you a number back, right? It's just a machine. Sometimes you know how this machine works. Sometimes you don't know how it works. You put a number in, you get a number out. So the graph is very nice for visualizing what a function does, but it is not a function, right? A function takes an input and maps it to an output. And this is important because sometimes it's very hard to visualize the graph of a function. Now, the inverse does the opposite. It in some sense undoes the function. And a lot of people were talking about this. So there's two ways we can think about an inverse. Okay, so the first way is it undoes the function. Okay, so a function takes an input to an output. The inverse says, you tell me what the output was, and I'll tell you what the input was. Okay, so a normal function takes an input and sends it to an output. Okay, but the inverse function goes the opposite direction. Okay, that's what we mean by undoes it. You give it the output and it tells you which input it came from. Does that make sense? Do people kind of understand that that's what the inverse is supposed to do? Right? Yeah. So it's like, you know, maybe this isn't a great analogy, but I think of it as kind of like a recipe sort of thing, right? Like, you know, I don't know. This isn't now, maybe the recipe isn't a great example, but a function is a machine. You give it an input, it turns it into an output. The inverse just kind of turns the conveyor belt around. And so if you give it the output, it turns it back into the input. So if I tell you, let's say you don't know what the function is, okay? I just tell you f is a function. And I tell you that f of 17 is equal to 25, okay? Eggs for cake, cake to eggs. Yeah, that's sort of the thing I was going for, Jack, but yeah, exactly, right? Eggs go into cake, and then the inverse would send the cake back to eggs. So let's try this as an example. If I tell you that f is a function and I don't tell you what it does, right? I don't tell you how 17 became 25. I just tell you that if you plug in 17, 25 comes out. What is f inverse of 25? Yeah, it's 17, right? Because it just undoes the function, right? It says, well, if 25 was the output, what was the input? Oh, the input was 17, because that's what I know from above, right? Okay, so now let's do the question, and then I'll tell you the second way of thinking about inverses. So remember, the question says the following. So our question says, we know that f of x equals x cubed plus x plus 1. What is f inverse of 1? Okay, so what we're asking, like, let's, right, exactly, 1 is the output. So we need to figure out what number gave us 1 as the output. Yes, I'll tell you what the second way of thinking about it is in a second. And we'll solve it the same way, right? So I'll tell you that in a second, yeah. Okay, so basically what I'm asking you, right? Like, let's think about it. I'm asking you what x of x satisfies right? I want 1 to be the output. So which x gives me 1 as an answer? And you don't have to do any fancy solving for this. You could if you want, but you don't have to do any fancy solving. Just if you had to look at it, what number works? 0 certainly works, right? Like if you plug in 0, so we see that f of 0 is 0 cubed plus 0 plus 1 equals 1. Therefore, f inverse of 1 is equal to 0. Okay, good, yeah. So I got a direct message saying x equals y cubed plus y plus 1 would be the equation to solve that. I mean, if you were looking for the inverse function, yes, right? But we specifically chose this function because you can't solve that equation for y. Yeah. Okay, good. So does that make sense? Everyone kind of sees that this is like, that's what the inverse does, right? Again, so if you think about it in a function in terms of input output, then that's exactly what it does. It says, give me the output, tell me what the input was. And so, right, this question isn't supposed to be tricky. And I think that if you look at the numeracy question now, for those of you who are maybe struggling with it, you're going to look at the numeracy question now and you're going to be like, oh man, that's not too bad at all, right? But whereas if you try and solve for the inverse function, if you actually try and compute it, that's a lot of work and it's not always going to be possible, right? Because you don't need to know what the inverse function is. I just ask you what number gets sent to the number 1, right? That's all you have to do. Okay, now the other way to think about it, which again, you don't need to know, or maybe let me make another comment here. You know, when you all say switch X and Y, notice that that's kind of what we're doing. This is, I hate, I will admit to you, I don't like this idea about switching X and Y, because what it does is it confuses what X and Y are doing. And a lot of students kind of, I think, get confused about the rules that X and Y. Yeah. So here, let me try and explain this. This one worries me a little bit. And if this is confusing you, please let me know. Let me try and think of a function which I can easily invert without too much trouble. Okay, so let's take a function. So let's do as an example, let's do something like f of x is equal to x over x plus 1. Okay, so hopefully this function is invertible. Can we find the function in terms of x just by looking? No, right? Because Rafid, the problem is that you don't know what the function is, right? So there's nothing like you can't do any manipulations to the function, because the only thing I told you about the function is that it maps 17 to 25. So there's just was kind of nothing you could do about it outside of that, right? Okay, so everyone, let me say the following. So if I set y, so I think this is normally how kind of people think about it, right? Y is equal to x over x plus 1. So first of all, strictly speaking, the thing on the right is no longer a function. It is a relationship between two variables, right? If I give you an x, you can figure out a y, for example. So I claim, for example, right, this is an equation, that the equation 1/1/2, or maybe let's say xy, equals 1/1/2 satisfies this equation. You all agree, right? If I plug x equals 1 into this equation, I get y equals 1/2 out. So if I were to plug x equals 1 into this and y is equal to half, I get a half is equal to a half. Therefore, this satisfies this equation, right? Now, the issue of switching x and y. So some people say, well, how do you solve for the inverse? Well, you switch x and y and solve for y. Let's do that and see what we get. Okay, so this is the switch x and y and solve for y. Okay, so if we do that, we're going to get x, is equal to y divided by y plus 1. So I'm going to multiply both sides by y plus 1. I'm trying to solve for a y, so I want all my y's on the same side. I'm going to factor out the y. And so I get y is equal to x divided by x minus 1. Okay, does everyone agree? Like that's how I think most of you have probably seen how to solve for inverse functions, right? So we'd say, therefore, thus f inverse of x is x over x minus 1. Right. Oh, and you can't, yeah, exactly. You can't find the inverse of some functions. Is it negative x? You're right, it is negative x. Thank you. Me just not knowing how to do math like that. Okay, everyone's good? Notice that this is not a solution to x is equal to y divided by y plus 1. Do you all agree? Because let's try it, right? Like what happens if I plug x equals 1 and y is equal to half into this equation? I would get 1 is equal to 1/2 divided by 1 plus 1/2. And this right-hand side is what? 1/3? Like this is clearly wrong. Right? Right? So what happens is when you switch x and y, you're changing the meaning of x and y. right? That's why I think that this is generally a bad way of doing this. When you do this, you've switched the meaning of X and Y. What you're doing here when you choose to do this is you're saying, I'm always imagining that X is the input variable and Y is the output variable. And because the inverse function flips those two things, right? The output becomes the input and vice versa. That's why it makes sense to flip X and Y, but you've changed the meaning of X and Y because the input variable for F is the output variable for F inverse, right? So you've changed what the meaning of X is in each of these cases. Nonetheless, you can see that this is what the inverse function is doing, right? It is interchanging the role of the input and the output for F. So this is the bad way to inverse thing? Not necessarily. I mean, again, in practice, this is kind of what you would do. What I would do personally, the way that I think is the better way of doing this, and it's structurally the same. It doesn't make any difference. But instead of switching X and Y, what I think you should do is just solve the equation for X. And it makes no difference. Watch, I'll solve the equation for X now, and I'll try and zoom out so you can see what I'm going to do. So what I'm just going to do instead is I'm going to start with the original equation, right, which is up here. So I've got Y is equal to X divided by X plus 1. And now I'm going to solve for X. Okay. And when I do that, what am I going to get? So I'm going to get, I go through the same steps. X, Y plus Y equals X. And then I'm solving for X. So I'm going to get XY minus X equals negative Y. And then I'm going to factor out the X. And then so I get X is equal to negative Y over Y minus 1. Okay. And you see, you get the same answer, right? It's just the X's and Y's are switched. You get the same answer. But the thing is, here, I haven't broken my solution, right? What did we say the solution was? We said the solution was XY is equal to 1, 1/2. Well, if I plug that into here, what do I get? I get 1 on the right-hand side. All right, so I get right-hand side. That's equal to 1. The left-hand side is what? So I'm going to get negative 1/2 divided by 1/2 minus 1. And look at that. That is equal to 1. Right? So when you don't flip X and Y, you're not breaking what X and Y mean, right? You're not changing what X and Y mean. And this might look a little bit weird to you because you're not used to Y probably being the input variable and X being the output variable. But this is a nice way of doing things because you haven't changed what X and Y mean. Okay, so are there any questions about that? Does that kind of make sense? Like maybe let me write it another way. So if Y is equal to F of X, then this means that F inverse of Y is equal to X, right? Like if you don't switch the role of X and Y, this is what we get. And this makes sense to us because we know that we're saying if you plug the output Y into the inverse, you should get the input back, right? So the blue, so in the blue, I still solved for one of the variables. I still solved for the variable that was on this side, like in the fraction. But in the yellow, I switched X and Y first. I just renamed them. And in the blue, I didn't rename them, right? I started with the original equation and just solved it for X. Okay, and so I want you to kind of look at this equation right here. This is what we did above, right? We said F of 17 was equal to, what did we say it was? 25? That's what I think it was, right? So here we're saying X is 17 and Y is 25. And therefore, F inverse of Y of 25 is equal to 17. Right? Exactly, yeah. It preserves what X and Y are. So does everyone see like why I don't like switching X's and Y's? Because I think it confuses students as to like what X and Y are really doing in that equation, right? You've changed what they mean. But I don't think you want to change what they mean to really understand what the inverse is doing, right? You want to say, if I plug the output variable Y into the inverse, I got out the input variable, which was X. Does that make sense? Are there any questions about that? Okay. And maybe just as a different way of thinking about it, sometimes I like to think about these as arrows, right? So if here's the inputs and here are the outputs, right? So you've got a bunch of inputs over here, and then you've got a bunch of outputs over here. And maybe F does this, right? The inverses are just to turn, the inverse function just turns the arrows around in the other direction, right? So F is the forward arrows, and then the inverse are just the backwards arrows. Okay, is everyone okay with that? I hope I didn't make things worse, but yeah, I hope that helped a little bit. If you think about it as a machine, it makes, I think, more sense rather than thinking about it in terms of a graph. Okay, so here, let's do another question. There was a second way of thinking about this. Maybe let's do the second poll question that I want to do here, and then I'll talk about that second way of thinking about the inverse because it's a little bit perhaps more related to this one. So with our newfound understanding of inverses, let's try the next one. Okay, so let's try this. Let me get the polls going in. Where are you? There you are. Relaunch. So we're defining a new function g is what we mean by here, right? So f already exists, and we're going to say g is this thing. So it's f inverse of x plus 2, right? So if I want to know what g of 7 is, it would be f inverse of 7 plus 2. So it'd be f inverse of 9. Okay, so it's slowing down a bit. I'm going to say 30 more seconds on this one. Okay, that's a pretty good turnout. I'm not too upset with that. So we're split a little bit, right? We're kind of bimodal here. Some people think it's A, some people think it's D, and there's a slight majority in D. D is the correct answer. Okay, so let's see why, and let's see, like A is close, right? Like I think it's probably not too hard to accidentally get A to be the correct answer, which means it's probably a good distractor. Let's give it a shot. Let me try and explain. Okay, so here's the second way of thinking about inverses. Okay, so number 2, this is the second way. Okay, let me just do it a different way. Okay, if we have that the inverse function flips input and output, right? The next question to do is to think about, well, what happens if I compose f with its inverse, right? So what is f of f inverse of y? What should that be? Yeah, it should be y, right? Or maybe I should have done the other way. No, this one's okay. So this is equal to y. And why is that? Well, let's think about it. So what I'm saying is we've got our inputs, right? We've got our outputs. So I start at y, right? Because remember, when you do function composition, you start with the inside function and then you do the outside function. Maybe I should have started with the opposite composition. Maybe that'll make more sense. But what are we going to do first? We're going to do the f inverse, right? So we're going to figure out what the input was. That's what f inverse does, right? But then what are we going to do? We're going to act f on that thing. So where do we end up? We end up back where we started, right? When you do f composed with f inverse, you start by going, oh, I've got the output. I'm going to go back to whatever input I needed, but then I'm going to take f of that thing, which is just going to send me back to the output, right? So I go from output to input, right back to output. Does that make sense? Is everyone okay with like how, you know, it goes one direction and then you turn the arrow around and you just come right back. So you end up exactly where you started. Everyone okay? Is there any questions about that? And if we do the opposite is also true, right? So if we do f inverse f of y, so again, we've got inputs. Sorry, this should be f of x. We've got outputs. So I start with an x over here. I do f of x. So I map it to an output. And then I do f inverse of that. And I say, oh, well, where did I come from? Oh, I just end up back where I started. Right? So I just substituted 4 into the inverse function is how that works. Well, let's see. Let's do it. So first of all, let's make sure everyone's okay with this fact first, and then I'll show you how I actually do the question. But is everyone okay that this is, again, what it just means by f inverse undoes whatever f did, right? F did something to x, and then f inverse undid it. And then f inverse did something to y, and then f undid that. So they kind of cancel each other out, right? Does that make sense? Can we just take rid of the f and f inverse? Like generally, yes. You just want to be a little bit careful about that. But yes, that is basically how it works. It's almost like an matter antimatter sort of thing, right? Like they touch each other and then they just vanish. Okay. So for this question, let's go back now and let's look at our question and what we were doing. So our question was, we had f is invertible and g of x was f inverse of x plus 4, well, x plus 2. I think it was x plus 2, right? And we said, what is f of g of 4? Okay, well, f of g of 4 is f of f inverse of 4 plus 2, right? Because this is what g of x is, right? It's f inverse of 4 plus 2. But the f and the f inverse, when they touch each other, they vanish, right? They cancel each other out. Like that. Okay, does that make sense? Yeah, right. F and so for the inverse isn't for the output. Yes. So I did x plus 2. Okay. Let's see if we can track this. Okay. So we're doing f inverse of so g of 4 is f inverse of 4 plus 2 is equal to f inverse of 6. Does everyone agree with that? Right? Because just in case some people are wondering like why I'm doing, there's still a couple of confusion. So g of 4 is f inverse of 6, right? Just by plugging x equals 4 everywhere. Okay, everyone's okay? So f inverse of 6 is whatever number sends f to 6, right? So basically what this says is that whatever this is, if I plug it into f, I get 6 out. This into f, we get 6, right? And so now if I do f of g of 4, that's f of f inverse of 6. But we said that whatever number this is, it's the thing that when we plug it into f gives us out 6. So it must be 6. Does that make sense? Especially for, the person who's direct messaging me who seemed to maybe still be a bit confused. No. So it's not that the output is 4, right? Remember, we have to be careful about this. Since g of x says figure out what mapped to x plus 2, right? So g of x says, let's figure out which thing mapped to x plus 2. So g of 7 would be what thing mapped to 9, right? And g of 1 would be what thing mapped to 3. So g of 4 is what thing mapped to 6, right? So it's not that the output is 7 or 1 or 4 because of that x plus 2 term. It's, you have to add the 2 to it, right? So I think most of the people who probably answered A kind of put the 2 on the wrong side. Like instead of figuring out what mapped to 6, they were trying to figure out like what mapped to 2 instead, right? Yeah. Okay, cool. Okay, so direct messenger asking me about the one-on-one office hours. That's TJ. TJ does that. Could we determine what f of x is from f inverse and go from there? Probably not, because you just don't have any information about f or f inverse, right? Like that f inverse exists, and that's pretty much it. And that g is defined in terms of f inverse, but you don't really know anything else beyond that. So really, this is the only way of doing this problem. Usually, there's a lot of ways that you can do problems, but in here, we just don't have enough information about what f is in order to be able to do anything. So we're stuck using the definition of the inverse in order to be able to say anything, okay? So the second way of thinking, so again, first way of thinking about inverses, because we're running out of time here. First way of thinking about inverses is that they, for a function, input maps to output, and the inverse reverses that. So you give it an output and it sends it back to an input. The other way of thinking about inverses is that when you compose them, they cancel each other out, right? So if you do f on something, it takes input to output, and then you compose it with f inverse, so then you take output back to input. Overall, what was the net effect is that the input just went back to itself. Nothing happened. And same thing, if you reverse the composition, output will go to input, will map back to input. What's the net effect of that? The output didn't change. It just went back to itself. So composing a function with its inverse, the functions just cancel each other out and you're just left with the thing that you plugged in to begin with. Okay, so that's a really useful and important way of thinking about what an inverse function does. Okay, any other questions about that? So an f is multiplied by f inverse. So not multiplied, we have to be careful about that, right? When they're composed, right? So f composed with f inverse of x is always just equal to whatever the input is, because I'm saying x goes to y, goes back to x. Mm-hmm. Yeah, we have to be careful, right? Multiplication is different. Yeah. Right, because multiplication is, you don't act two functions. If you were to do, what do I want here? Yeah, we're not multiplying, right? Those are really different things. We just have to be careful about that. So kind of like how we have f of x, here we have f of f inverse of x. Exactly. Yeah, that's exactly it. Okay. Everyone's good? So we didn't get too many questions out today, but I think it's okay because we did a lot of, we talked about what functions are, and hopefully, we had some insight into like how functions work and how we can use them, which I think is an okay trade-off. We're going to go into office hours now. Exactly, yeah. Of usually denotes function composition.
As you go to office hours, I'm going to go start my tutorial at the same time.
Okay, sounds good. So I have a couple of requests here of stuff to do. Maybe I might just take a couple of minutes though, refill the water and stuff. Let's get a little low. But let me pull it up. So the loaded die question, so direct messenger, you probably meant the assignment question, loaded die question. Is that what you meant? Like question one where, well, I guess that's a coin. So a lecture from last week? So like one of the poll questions? Okay, let me see. Do you remember which poll question it was? Because there's probably a couple loaded die. Let's see. Sure, okay. Yeah, here, let me just maybe hit these two off and then I'll take a quick break. So numeracy 3 and a loaded die question. So I'll see if I can find the loaded die question and or I'll just make one up. Over the question one with bias die. Okay, so so a couple of people are asking about the loaded die. So I'll talk about that one. Let me do numeracy 3 maybe first because I've been asked on that one a couple of times. So direct messenger asking me about numeracy 3. So numeracy 3.2, we kind of talked about how to do that. So is it numeracy 3.1 that's bugging you? Yeah, okay. So here, maybe we can do a similar one together as a class, but not the same one, obviously, right? So let's do a similar one. So let's say I tell you that f of x plus y is equal to f of x plus f of y, okay? So notably in, okay, here, let me write these down because I'm starting to get a bunch of requests. And then 4.2 from the text. Okay. All right. So let's say instead I told you that f of x plus y was equal to f of x plus f of y. Okay. So in the numeracy question that you have, it's multiplication, right? It's not addition. So what could I do? When I write this down, remember y isn't the output of the function, it's just some number. So what I'm saying by this is that if I do f of 7 plus 3, that's the same thing as f of 7 plus f of 3, right? If I can write my number there as x plus y, then I can break it up and write it as f of x plus f of y. Okay, sure, an algebraic description of a function, sure. So if I want to know what f of 0 does, what numbers do you guys want to choose for x and y? So somebody give me some good candidates for x and y here. Y equals, okay, yeah, 1 and -1, y equals negative x, 3, -3. Okay, lots of great choices. People doing lots of cool things. So let's try f of 1 and -1. So f of 1 plus -1. So that's f of 0, right? So if you don't use this relationship and you just do 1 plus -1, that's 0. And so for those of you who are saying 3 and -3, it's the same sort of story, right? And that would give me f of 1 plus f of -1. Okay, so that's kind of cool, right? That gives us something to do with f of 0. Ah, yes. Okay, so somebody in the direct message gave me a really good one. So, I mean, we could play with this a little bit more and see what we can do with it. But somebody in the direct messages suggested, well, what if you let x and y both be 0? Okay, so what happens if we do this? Well, we get f of 0 plus 0. Well, that's just f of 0, right? Nothing crazy there. You just add 0 plus 0, you get 0. And on the other side, I'm going to get f of 0 plus f of 0. Oops, that's doesn't look right. Okay, and so in total, what do we have here? So we've got that f of 0 is equal to f of 0 plus f of 0. What must f of 0 be? If I were to like solve this equation for f of 0. Yeah, it's 0. Right? Does that make sense? So we were actually able to use this property of the function in order to be able to determine what f of 0 actually was. And you're going to do something very similar for numeracy 3. Okay. Actually, I want to answer a question. Stanley, are you still here? Okay, well, Stanley, I don't think is here anymore, but I still want to answer his question anymore, which I can then just refer him to this video. So Stanley asked a great question, which is the inverse function related to inverse matrices at all? So Stanley, if you ever come back and watch this video, here's the relationship. And the answer is yes. You can define a function like this, and in which case the inverse function is given by the inverse matrix. Oh, is it? Okay. Oh, so did Connie change the name? No, Connie didn't. Okay. Well, either way, Stanley and or Connie, if you ever see it. Oh, I see. Okay. But I don't think Connie's here anymore. Like she, I think, isn't in the participation list. But Connie, if you ever see this, yes, they are related to each other. The inverse, if you define a function using the matrix, then the inverse function is actually the same thing defined using the inverse matrix. Okay, so that turns out to be a cool thing that, yeah, ends up being true. Okay. So does this answer enough about numeracy 3.1 that everyone is okay with kind of at least where to start and where to try? Yeah, okay. So if you, there's kind of a similar question that's in my backup list of things to come back for. So yeah, numeracy answers can vary for sure. Numeracy 3.1, there's really only three. For numeracy 3, there's really only one answer. But for numeracy 4, there are definitely not a lot of options. So if you let me maybe hit your answer up, because there's a couple of people who've direct messaged me with something similar. Give me, everyone, give me maybe like 2 or 3 minutes here. And then, so Kelly, is that from the assignment? Okay. So everyone, just give me like 2 or 3 minutes here. I'll be right back. And then, I'll answer all your questions. Okay. So like 2-3 minutes at most. I'll be right back. Okay, let's see. Agama, I don't know what you're asking for, Brandon. No, yeah, that one's not allowed for 3.2. For 3.2, you should do it the way we talked about in class. Don't use like Desmos for that. Okay, so let me start the one I was doing for 3.1. Oh, like my example. Yeah, so I mean, you could keep going here. I'm not 100% certain what you might like. There's from this equation, f of 1 plus f of -1, there might be more stuff you can do, but like the much easier solution is just to let x and y be equal to 0. That doesn't mean that there's nothing else you could do, just that that's the easiest one. In fact, if you let x be 0 and y be 1, there's some easier things you can do there. Yep. Yeah, Namir, actually somebody else exactly asked that question as well. So let me start going through the questions that I have. So the first question was a loaded die question, or maybe, okay, let me maybe answer the things I can do quickly first in case anybody needs to run. So a question that people have been asking is, what do I mean by algebraic description of a function? So I've gotten that one a couple times. It comes up in numeracy 4, right? What I mean by an algebraic description is, how do I describe this? It is a description of the function which uses algebra, and you're like, no, duh, obviously, but is such that you can compute the value of the function at any point completely and totally unambiguously. Okay, so let me give you an example. So let's say I gave you this function. Okay, and let's say that it was like, you know, here's 1, here's 2, 0, -1, -2, like that. Maybe let's even extend it a little bit just so we can kind of see the pattern. 3 and 4. Okay, and let's say that the function was like this. So it was, you know, 0, and then it was 1, and then it was 0, and then it was like 1, like that. Okay, let's say this is height 1. And it just kind of continued in this pattern forever. And you can see that's kind of similar to what you have to do in the question. The question is obviously numeracy 4 is a little bit more complicated because you actually have like, you know, this sawtooth motion instead of just constant functions. But how would you describe a function like this? Well, you could use like an infinite piecewise function, but it's kind of hard to write infinite, you know, curly braces. So the way I would do this is say something like following. I would say, okay, what's sort of the pattern here? So it seems to be 0. The function is constantly 0 on 0, 1, on 2, 3, and on, you know, 4, 6, and everything like that. Okay, so how would I algebraically describe this? Oh, the first number is always even, right? So I'd say something like, you know, if x is in 2n plus 1, then f of x is equal to 0. And if x, like, let's maybe say there's a hole here and here. And if x is in 2n what do I want? Plus 1 to 2n plus 2, then f of x is equal to 1. Does that kind of make sense? So, and here 2n and 2n plus 1 are playing the role of like the numbers even and odd. So for example, when n is equal to 0, right? Like what I'm trying to do here is capture 0, 1. So when n is equal to 0, this interval here becomes 0, 1. When n is equal to 1, if I were to plug n equals 1 into this equation, I would get 2, 3, right? When I plug n equals 2 into this equation, I get 4, 6, and so on. So this is an algebraic description of this function, which is completely and totally unambiguous, right? If you give me a number, you say x is equal to pi. I'd say, okay, well, is pi in an interval of the form even to odd or odd to even? Right? I'd say, oh, it's about 3.1 for 1. So, oh, it's in this thing, and therefore f of x is equal to 1, right? Could we put in a function at the end? So like, yes, absolutely. Yeah, Brandon, 100% you could do that. Okay, and if you're having trouble like, oh, how do I use 2n and 2n plus 1? You're totally allowed to say, suppose that it's in an interval a, b, where a is, or maybe like a plus 1, where a is even, or a plus 1, where a is odd. You know what I mean? Like, you're perfectly describing, I don't know, but I guess you guys are just so used to watching the video, right? You want me to stop and like think about what I was saying. But does that make sense? Like, if you don't want to use 2n and 2n plus 1 and this sort of language, you can say a to a plus 1, right? You're saying a number to its next number where a is some even, you know, like you should probably say even integer here or something. Does that make sense? Yeah, it's basically like I'm writing a piecewise function, right? Instead of just saying like explicitly what each interval is, instead I'm kind of saying like, here's what the interval looks like. And if it looks like this, then your function is going to do this. And if it looks like this, then your function is going to do that. Right. So they're just, it's very similar to a piecewise function. You're just kind of being more general than that. And you can imagine, based off of the function that you've been given, it repeats pretty quickly. So you don't have to specify too much information. And it's very similar to even kind of what we did here, where it's probably going to change depending on whether your interval starts with an even or odd number, right? So this should hopefully help you a lot, and that'll give you a good start to numeracy 4 and tell you what it means to give an algebraic description of a number. Okay, so does that answer everyone's questions? So somebody asked me like about numeracy 4, or someone asked me about what the algebraic description of a function is. Does that satisfy both of those? Oh, Dad, I can't tell if you're answering Brandon or answering me. Okay, cool. Sure. Yeah, I mean, listen, like Brandon, if you're confident that you could do this but it was posted. I actually think I posted it on Wednesday, but in theory, I was only going to post it on Friday. So, you know, worst case scenarios, it's only been up for a couple days anyway. But, you know, I would say there's 4 questions to it. So don't leave it for too long, right? Don't kind of push it to last minute. So for question 2, can I answer it by explaining my steps without defining random variables in sample space? You can do it without, yes, I'd say that is okay. So for question 2, because it's asking about expected value, if you don't want to, you don't have to define the random variable. I think it's nice to do, but strictly speaking, you don't have to do. And very often, even when mathematicians do expected value questions, we don't explicitly write down the random variable. That's okay. But yeah, if you want to do it just by explaining your steps, that's totally okay. And Rafi, does that actually answer, is that what you were asking about question 2 in the first place? Like, okay, so I don't need to worry about that anymore. Okay, cool. Okay, loaded dice question. So for those of you asking about loaded dice, do you have an example? Oh, okay, sure. Let me talk. So sorry, I got a direct message saying confused about what I wrote here. So can you elaborate what about here maybe is confusing you, and I can go into it in more detail? The if lines. Okay, sure. Yeah, loaded die and biased die are the same thing. The if line. So what I'm trying to do, you know when you write a piecewise function, like if I write something like f of x equals 0 if x is in 0, 1, and 1 if x is in 1, 2, or let's say maybe open 1, 2, right? So a piecewise function is telling you, it's giving you a bunch of cases, right? It says, and how do you actually check those cases? Well, you first look over here and say, am I in this case? If so, do this. If I'm in this case, if so, do that. And when I write, let me just maybe highlight what I'm doing here. If I write this, I'm basically doing the same thing, but instead of saying 0, 1, I'm saying if you're in any interval that looks like this, then your function does this thing. And if you're in any interval which looks like this, then your function does this thing. Does that make sense? Like it's specifying the cases to look at in exactly the same way that a piecewise function tells you a bunch of different cases, and you determine which case you're in order to figure out which function to use. Is exactly what we're doing in the yellow box as well. I'm saying here are the cases, and once you determine which case you're in, here's what your function does. I don't know. Okay, hold on. I want to be careful. I don't want to just say like yes here because you said, oh, because we have two y values. I don't know. We have two different functions. Yes, that is what that means. I think I understand what you're saying. You're right. We have two, like the function seems to be behaving in two different ways depending on where I am. And so I'm trying to break that into cases, right? And I think that's what you mean by two different y values. Yeah, exactly. Yeah, exactly. So that's what I'm doing. As I'm saying, the function seems to have fundamentally different behavior depending on what sort of interval I'm in. So I'm going to say, if you're in this interval, your function behaves like this. And if you're in this interval, your function behaves like that. And, you know, you just do that as many times as you have to. Okay, cool. The domain is larger than the interval shown. Yeah, the domain is, it says, consider the function f defined on the real numbers. So the domain is all real numbers, and the graph is just shown on -3 to 3. So the graph is all real, or the domain is all real numbers, and you have to say, you know, how would you compute this function for all real numbers? But it just repeats in that pattern forever, right? But you therefore have to say, how do you compute f of x for any real number x? Why are the brackets of the two functions different? Sure. So they're just different because you can't, like here, what would go wrong if I made these a square bracket? Well, look, these are the same, right? These numbers could be equal, but you can't be both equal to 0 and 1, right? A function can't take on two different outputs at the same time. So I just use these brackets to indicate that there are these holes here, right? That it's equal to 1 everywhere up to 2n plus 1 and 2n plus 2, but not when we're equal to 2n plus 1 and 2n plus 2. Does that make sense? Cool. If the line is diagonal, like in the assignment, do you define the function as between the two numbers? And the line is crossing. It depends. So there are definitely a couple of ways of answering this question. It's kind of up to you, but Jack, if you want to refine your question a little bit more, because I'm not quite certain by what you mean by as between the two numbers the line is crossing. So if you can elaborate on that one a little bit more, I can answer it. But there are a couple of ways of doing this question. There isn't like one, just one way of doing it. Oh yes, you're right. I wrote 4, 6. Thank you. Yeah, that should be 4, 5. Yeah. Okay, in the meantime, while Jack's kind of refining his question for me, did anyone find a loaded die question or a biased die question? No one? I can just make something up, but like the question is for those of you who want a loaded die question, like what do you want about that question? Do you want like a conditional probability thing? Do you want expected value? Sure. Here, let me just zoom out. Maybe that'll help. Conditional probability. Okay. Okay, let me then do, maybe let's do kind of like a standard question where I roll 2 dice, but one of the dice is loaded. Question 4. Okay, sure. Yeah, okay. So let's do question 4 then. So question 4, this is fall week 11. Right? So the question, if you don't want to pull it up, so it says roll 2d6. This one, okay, so we need a biased dice, right? Okay, sure. So let's give them different names. So roll a blue die, and let's say a red die. Okay, so red dice, or let's say blue die is fair. And red die, let's make something up. So red die has the following probability distribution. So let's say, I don't know, it comes up 1 and 2 a third of the time. And then, so what do I got left? So I have 1/12 if x equals 3, 4, 5, or 6. And that should sum to 1. I'm pretty sure that's a good thing. Okay, Jack, sweet, awesome, good to hear. Okay, everyone agrees that die is makes sense, right? I think the probabilities all add to 1. I don't think I'm crazy there. And then let's let B is, or let's let E be the event. First, or let's say blue die is odd. And F is the event. Oh, sorry. Sum is even, and then blue die is odd. Okay, does that sound like a good question? Will this satisfy the loaded die, bias die question for those of you looking for it? All right, let's compute the probability of F given E or something. Okay. So this is a pretty complicated question. There's a lot of stuff going on here. Now, by definition, okay, so this is just our setup. So as our solution, so we know, okay, what is the probability of F given E? How do I compute this? How do I compute conditional probabilities? Nice autocorrect. I like it. I like it. So yeah, we could do Bayes' theorem. I think this one actually is not too hard to do on its own. We could try doing Bayes' theorem afterwards if you want, but I think this one we can actually do directly. So if I wanted to do it directly, what would we do? Anyone remember what the conditional probability formula is? Oh, its sum is 7, not even. No, let's do even. Okay, yeah, beautiful. So it's the probability of, how did you write it? F intersect E divided by the probability of E. Perfect. Okay. Okay, so no, direct messenger. So that would be true if the events are independent. And the thing is, we don't know if they're independent or not, right? Like if you can sort that out ahead of time and you know that they're independent, that answer is correct. If you compute it this way, and the events are independent, you will actually get this, you'll still get that answer, right? So somebody, direct message said, oh, it's the probability of F times the probability of E. That is the correct answer if the events are independent. But if you don't know, you can compute it this way. And even if they're not independent, you'll get the right answer. And if they are independent, you'll still get the right answer, right? No, loaded die doesn't mean the events aren't independent, right? Like, so for example, if I say, what's the probability that the loaded die rolls a 4 if the first die is a 1? Well, the outcome of the first die does not affect the second die, right? They're not the same die. So if I roll the first die, that doesn't have any effect whatsoever on how the second die rolls. So being loaded does not necessarily mean the events are not independent. In fact, the events should basically be independent or not, regardless of whether the die is loaded or not. Yeah, we can. Like, I'm going to draw it out just because I think it's going to make our lives a little bit easier. So let me draw our kind of typical table. Again, I would always draw this out just because for me it's a little bit easier to see what's going on. 4, 5, 6. Let's let this be the blue die. So this is the fair die. And then let's 1, 2, 3, 4, 5, 6. So this is the red. Okay, you're all gonna have to give me a second because I have to fill in my table. I usually, when I prep for a lecture, I usually just have this table made ahead of time and then I just copy and paste it, right? But okay. So let's see. Let's make E. E is going to be blue. Okay, so I need the even events. And I realize I've made a terrible mistake because this event is going to be terrible to compute. 6, 8, 10, 8, 10, 12. Right. Okay. I've made a huge mistake just because I've made a lot of work. How do we know when we can use a table and for what questions a table wouldn't be a good idea? I mean, I think a table is always useful as long as it's reasonable to write out the table. You know what I mean? It's sort of a thing that you kind of have to make your discretion of. So for example, if I said roll 3 dice, that table is really hard to draw because it's like a 3-dimensional table. That table is probably not worth drawing out, sort of thing, right? But I'd say anytime it's reasonable to make a table, you should just do it, right? Just like anytime you can draw a picture, you should do it. Even if the picture doesn't help, sometimes it does help to organize your thoughts and help you visualize things. You should just always do it if it's possible. And I think that's generally a good piece of advice. Okay, so okay, even sum is blue. Let's now do, what did we say F is? The blue die is odd. That was a huge, I should have used different colors. Blue die is odd is these ones. Right? Well, if the probability is 1, that means it's guaranteed to happen, right? So probably the probability isn't 1. So we're saying, okay, assume that the blue stuff has happened. What's the probability that the green stuff has happened? And normally what we would do is, let me see, what's the probability the blue die is odd given that the sum is even? So we'd say, yeah, we would say which things are both blue and green, and then we would divide that by the total number of blue things, right? If the probability were fair, that's how we would do this problem, right? We would say, what are the things which are both blue and green, and divided by the total number of blue things. Now, the problem here is that we can't do that. And we can't do that precisely because the die are not fair. So we actually have to compute the probabilities of each of these events separately. And again, I've made a huge mistake because E has a large number of events in it. Okay, so let's say I did this question anyway. The red die is 1/3 if X is equal to 1 or 2. Okay, so all right, here's what I'm going to do. I'm going to, yeah, this was a mistake. 1, 1. So E is equal to 1, 1, 1, 3, 1, 5, 2, 2. And you'll see, I'm going to draw this in a special way so you can see it in a second. 2, 4, 2, 6. Okay, these are special. And then 4, 1, 4, 3, 1. 3, 3, 3, And again, like this is how you do it if you couldn't draw the table out, right? I think that would help carry on to being able to do more complex problems. Exactly, exactly. Yeah, so, and actually, so there's a follow-up question, which is how would you solve this without a table? So I'm actually going to show you the other way that you would do it, which is just to write out all the possibilities. 3, 5, 5, 1, 5, 3, 5, 5. And then, oh, damn it, I missed the 4s. So 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5. This actually, I would just do it using a sum instead of writing them all out, but I think most of you probably don't like sums. So I think it's worthwhile just to do this one that hard way. Okay, and now here's what I would say. I would say, let's compute the probability of this group of things separate from this group of things. Okay, and when I do this, I'm doing red die, blue die. That's the order here. Okay. Okay, so the probability of everything in the first, yeah, exactly, Rafid, thank you. You seem to, I always seem to like do it, and then you've already said it in the chat, and I've, right, but like, exactly. Okay, so in the top table, let's call these things, these are my star group, right? What is the probability of any event in the star group? Did I write 6, 6 twice? Oh, I did, sorry, that should be 6, 4. What's the probability of anything in the star group? Can anyone tell me? Like they're all the same. The probability of everything in the star group is the same. Okay, close. So that's the probability of getting the first thing being a 1 or a 2 is a third, but I have to multiply that by the probability of the second die, right? So here, let's compute. What's the probability of 1, 1? That's the probability that the red dice is equal to 1 times the probability that the blue dice is equal to 1. What is that? So the red dice being equal to 1 is 1/3. The blue dice is fair, right? So what's the probability the blue dice is 1? 1/6, perfect. So that gives me 1/18. Does everyone agree? Is that okay? And everything in the star group is the same calculation, right? Because the red die is either 1 or 2, and those numbers both have the same probability. And who cares about the blue die? Those are always all the same, right? So everything in the star group in star has a probability of 1/18. Okay, how about the non-star group? So if you're not in the star group, what's the probability? All right, if you're not certain, you can do an example, right? Probability of 3, 1. Probability of the red die is 3 times the probability of the blue die is 1. Yeah, great. So 1/12 times 1/6, which is 1/72. Okay. Now the probability of E is therefore, it's the sum of all of these probabilities, right? And there are a lot of things in here. What is there? There's 18 events. I don't want to add them all up. So what I'm going to do is I'm going to say, listen, there are 6 events with probability 1/18. And there are 12 events with probability 1/72. Is that step okay? Do I need to break that one down a little bit more? Or is everyone okay with what I did there? Because I'm happy to break it down more, but let me know. Okay, sure. So the probability of E is the probability of every event in here, right? So this is the probability of 1, 1 plus the probability of 1, 3 plus the probability of 1, 5. Okay, now I'm not going to write down all 18 things, right? But what I'm going to do is I'm just going to write down all these probabilities plus the probability of 6, 6, right? So pretend that I wrote down 18 of those things. Okay. Everything in the star group has the same probability, right? So that means that I'm going to get, 1/18 plus 1/18 plus ... plus 1/18. I'm going to get that for the number of things in the star group. Does everyone agree? And that's just the star group. I've only done the first 6 numbers, but that's the probability of everything in the star group. So I get 1/18 times 6 times, right? And then I'm going to get 1/72 plus 1/72 plus ... plus 1/72. I get one of these for every single thing in the non-star group. So that's going to be, I'm going to get that 12 times, right? And if you add those up, that gives you 6/18 plus 12/72. Okay, is that good? And right, we could simplify that a bit more. What is that? That's 1/3 plus 1/6. So that's 2/3. So the probability of E is pretty high. Did you get a half? Did I screw it up? Somebody double check my math here. 6/18. So that is 1/3, right? 12/72 is 1/6. So that's 3, 6 plus 1/6 is, oh, no, 2, 6 plus 1/6 is, yeah, never mind. I can't add fractions. So 2, 6 plus 1/6 is 3, 6 is a half. You're right. Okay. And now we need to do the probability of E intersect F. So what is E intersect F? So we're going to go back up to my table, or again, we could do it without a table and just kind of, use our brains. So everything that is both green and blue, right? So blue die is odds, the second die is odd, and the sum is even. Blue die, the second die is odd, and blue is even, right? Okay, somebody help me out here. So this is going to be 1, 1. Second die is odd. 1, 5. And the sum is even. So this is going to be 1, 3, 3, 3, 5, 3, and 1, 5, 3, 5, 5, 5. Is that right? Pretty sure that's all of them. Can we count it for the sample space of E? So actually, it turns out there is an easier way of doing E, and the answer for E is that the events are they're basically independent. So it's really just what is the probability that yeah, why does that end up working out to just be a half? It's because it shows up. So E is the sum is even. Yeah, I need to think a little bit more. In this case, it's not as obvious to me that the probability is directly equal to a half, but there must be some sort of slick probabilistic reason why we could have just gone straight to that answer. Yeah. What did I count twice? Yeah, Rafid, exactly, yeah. Brandon, which ones did I do? Oh, I did 1, 3 twice. You're right. Sorry, that should be, oh man, what am I doing here? So this should be 3, 1, 3, 3, 3, 5. Sorry, I'm just not using my brain. 5, 1, 5, 3, 5, 5. Right? Okay, there we go. That's fixed. Yeah, the events aren't equiprobable. That's why we just can't do the counting, right? And that's why people wanted to do the loaded dice example, is because, yeah, you can't just count it. Because if we could just count it, I could just go up here and look at this and I would say, okay, listen, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 things in E intersect F, right? That has 9 things. And then E just has what? 18 things. So the probability of the whole thing would just be a half. It would be 9 divided by 18. So if they were equiprobable, that's how we would do it. But because it's not equiprobable, it's a lot more work. And we have to actually compute the probabilities of everything. Okay, so again, we have to compute the probabilities of everything here. Again, we have a star group, right? And then a non-star group. Now we've already computed the probabilities of all the things in, maybe I haven't gotten there yet. So let's try it. So the probability of E intersect F is going to be what? 3/18 plus 6, 72. So what is that? 1/6 plus 1/6. So did I mess that up? 1, 2, 3, 4, 5, 6, 6 over 72, 3 over 18. So that would be 1/3. Does that look right? See you, Daniel. You got 1/4. Okay, how'd you get a 4th? So 1/18. Did I just screw up by adding of fractions again? Oh, because 6 over 72 is a 12th. Wow, fractions are not doing it for me today, right? So 3/12 is a 4th. Yeah, you're right. Yeah. Yeah, today I just can't add fractions. Okay, and so now the conditional probability, the probability of F given E is going to be 1/4, or sorry, it's going to be, yeah, so it's going to be 1/4 divided by 1/2, which lo and behold is a half. So actually this question was, the events were not interesting because we got the same answers as if the events were not, or if the events were equiprobable, we got the same answer. But for those of you looking for a loaded die question, does that make sense on how you do it? Like you can see, it's a lot more work, right? Because you have to figure out now what the probability of every single thing is. Right, so what I would have done is I just would have counted to myself, and this is kind of a more advanced thing, but what I would have said is I would have actually said, okay, E, what is the probability that the sum is even? Well, I just immediately know that half of the events are even. So what I'm going to do now is say, well, how many of those events have the red die being 1 or 2? And then I would have written them out. So I would have said, okay, how many events occur with the red die equaling 1 or 2? Okay, so if the first die is red, or sorry, if the red die is 1, the second die has to be an odd number as well. So there are 3 of those. If the red die is even, the blue die also has to be even. So there are 3 of those. So there are 6 events. The probability of each of those events is 1/3 times 1/16 is 1/18. So that means there are 6/18 probability where the red die is 1 or 2. And then I would have done the same thing with the non-red dies. So basically, instead of writing them all out, I just would have basically counted them and then multiplied them by what I knew their probability to be. This is a technique that requires a lot more explanation. Like if you're writing it down as an answer, you really have to explain what you're doing in every portion. But yeah, that's how I would have done it without writing everything down. Does that make sense? Okay, I have to turn off the transcript because it's not, like, it's just really killing my computer. Unless me not saying anything. Did I hide the transcript? No, it's still killing my computer. Oh man. Yeah, I gotta turn this off. All right, immediately my computer works better now. Okay, let's see. So a summation could be used here. It absolutely could. I haven't looked at the assignment yet, but would we need to, like, what do we need for it? So you need functions and then conditional probability and expected value. So a lot of the function stuff that we did today, for the summation, no, you don't need to do it by summations. I don't think any of the questions that we gave you need summation stuff. You could avoid it pretty easily. How do I get 1/12 for the red, blue in the non-star group? Okay, sure. So there, for this one, for E intersect F, Sean, is that the one you're asking about? Okay, yeah. So each of these things, right, like the probability of 3, 5 is the probability that the red die is 3 times the probability that the blue die is 5, right? And that's going to be 1/12 times 1/6 equals 1/72, right? So that's the same calculation that we did up here, right? So everything in non-star has a probability of 1/72. And then when we're computing the probability of E intersect F, we'd say, well, how many things are in non-star? Well, there's 6 of them. So that means I'm going to have 1/72 plus 1/72 plus 1/72. I'm going to have one of these for every non-star thing. i.e., I have 6 of them. So if I have 1/72 plus 1/72 6 times, that gives me 6 over, sorry, why is this 72? That gives me 6/72. And that's equal to 1/12. Does that make sense? So the 1/12 is after I reduced it from 6/72. And the 6/72 is because there were 6 non-event, non-star things divided by or multiplied by 1/72, which is their probability. Cool. Okay, so loaded die people, are you kind of happy with that? It was a little, involved, but loaded die stuff tends to be. Because you just have to compute the probabilities of everything, right? It's not as easy as when it's equiprobable. No problem. Okay, somebody asked example 4.2, but I think they said from the conditional probability portions, but 4.2 is much earlier than that. So whoever asked that, can you remind me of which example you wanted again? 420, okay, I see. Suppose you're given 2 bags, oh no. Okay, so this is example 4.20. From the notes. Yeah, it looks like conditional probability and the law of total probability, right? So it says, suppose you are given 2 bags. The first bag contains 2 white balls. Always draw your pictures, right? So bag 1, so it has 2 white balls. And, and a black ball, okay. And a black ball. Okay, and then second bag is 2 black and 2 white. So we got 2 white and 2 black. Okay, you select a bag at random and you choose a ball from the bag. The ball is then placed in the other bag and a new ball is chosen from the bag. What's the probability the ball is white? Okay. Yeah, so you can see in this example that we made a decision tree because the decision tree is just definitely the easiest way to do it. And basically what the solution is saying is that, let me see how I can explain this. Okay, first of all, let's just build the decision tree and make sure everyone is okay with it. So what are the steps? So step 1, choose a bag at random. Right? Step 2, choose a ball from that bag. And put it in the other bag. And then step 3, choose a ball from the other bag. Okay, so here, what you want to do is you really want to draw, again, your decision tree. So what I'm going to do is say, all right, the first decision that we have to make in step 1 is we have to decide which bag we're going to choose, right? So with probability 1/2, I choose bag 1, and with probability 1/2, I choose bag 2. Is everyone okay with that? I should really move this down because I need to draw more limbs. Okay. And again, this is just a nice visual aid to help me keep track of what's going on. Yeah, exactly. It's a half because there's 2 bags and I assume that there's equal probability. If there were 3 bags, it would be a third. If the bags didn't have equal probability, maybe it's like, 3/4 for one bag or 1/4 for another. But right now, 2 bags, it's equiprobable, so it's a half for each bag. Okay. Okay, so if I choose bag 1 now, right? So I'm looking at bag 1 and I reach into that bag, I can either pull out a white ball or a blue ball, or sorry, a black ball. White or black, right? What's the probability that I choose a white ball if I pull it from bag 1 and assume, again, all probabilities are equal? Right, 2/3, exactly. That means that black ball is 1/3, right? Wait, Curtis, I don't know if you were anticipating 1/3 for the next, right, okay, yeah. Okay, so now what I do is so now let's work on this tree. So I chose a white ball and I put the white ball in bag 2. So bag 2 now has 3 white balls and 2 black balls, right? So what's the probability that I choose a white ball in bag 2? 3/5, exactly. And 2/5 for a black ball, right? And we can continue to do this sort of thing. You can see there's like a lot, right? That's just how combinatorics work. And Emma and Brandon, exactly. Same thing, if we had chosen a black ball and put it into the bag, then our bag, would look like 2 white and 3 blacks. And so our probabilities would be 2/5 and 3/5 for white and black. And then if we had chosen bag 2 instead, we can do the same sort of thing. White, black, white, black, white, black. This is 50-50 for each. If I choose a white ball and put it in there, this should be 3/4, 1/4. If I chose a black ball from bag 2, it'd be 50-50, I think, 1/2, 1/2. And then let me check my decision tree. Yes, that is right. I just put white and black in the opposite order. Okay. You just pick one ball. So once you've chosen the bag, you choose one ball from the bag that you chose, put it in the other bag, and then you choose one ball from the other bag. So it says exactly how many balls you choose each time. Okay. And then basically I say what you basically want to do now is trace the tree. Okay, so let me get rid of these. So now we're asked, what is the probability that you choose a white ball? And so what you want to do is you want to look at all the ways that you finished with a white ball, right? So here's one way that you finished with a white ball. Here is another way that you finished with a white ball. Maybe I should do this in a slightly different way. So here's one way, right? Here's another way. Here's a way. And here is a way. Okay. And so the probability that you chose a white ball is going to be the sum of all of these probabilities, because that is how the law of total probability works. And then the final probability, like basically if you ask, what is the probability that I took this chain of events, is 1/2 times 2/3 times 3/5. Okay. And if I said, what is, the probability that I took this chain of events, it's 1/2 times 1/2 times 1/2. Right? So you just multiply the probabilities along every branch of the tree. And then you add up all the branches of the tree. So there are 4 branches of the tree that you have to add up. And you compute all their probabilities and you add them up and you're done. Now, the solution explains to you why you add them up and why you multiply the probabilities. And that's related to conditional probability and the law of total probability. But we're running out of time here. So that's the gist of how that works. When you make a decision tree, if you want to figure out the probability of each leaf at the edge of the tree, you just multiply the probabilities along the path, and that will give you the probability. And then you add up all the answers. If you want like a more detailed explanation behind why we multiply the probabilities and why we add them up, the reason why we multiply them is because that's how conditional probability works. And the reason why we add them is the law of total probability, right? Okay, so we multiply, so each event is the product of the probabilities along its path, right? The reason for that is conditional probability, namely that the probability of A is equal to the probability of A given B times the probability of B. Is that what I want? No. What is this one again? A given B is the probability of A given by the probability of A. Yes, this would be the probability of A and B. Okay, and then 2 is that you sum them, sum all possible paths. And the reason for that is the law of total probability. Okay. No problem, Jacob. So everyone, like what you can do is you can give that a read. And then if you want to talk about it more or ask about it on Piazza, I'm very happy to do it there, but maybe give that a read first and see if now that I've explained it, if you can parse that and if that makes sense. But yeah, basically it boils down to using both conditional probability and the law of total probability. All right, everyone. No problem. Yeah, see everyone on Thursday. Hopefully everyone's good. Yeah, sure. No problem. See everyone. Same, what's up? As a quick question. I saw you, don't worry, I'm not leaving. How come the answer to the example does this? Like, how come we're ignoring black on the second draw? Is that what you're asking? Like, why do we not look at B? I mean, so the question says, what is the probability that the ball is white, right? That the second draw ball is white. So we don't care about whether black is in the second draw at all. Like really, if we, even in our decision tree, we could have skipped it because we don't care if the second ball is black because that's not the probability we're trying to find. We only care if the second ball is white. Right, so that's why every time I trace a path on this tree, it's to get to a white ball in the second draw. Does that make sense? Okay. Oh, and I see. And it says black on the second draw. I don't know. Maybe this is a typo. Maybe the question was originally black and it got changed to white. Yeah, I see what you're saying. I see what you're saying. Okay, let me give this a reread and determine if I've just made a mistake, like if that's a typo and it should say W second draw or whatever. Let me reread it and I'll get back to you. Yeah, it could just be a typo. Yeah, okay. No problem, no problem. And Kelly, question 2 on the assignment. Right, so what part of question 2? Can you be more specific about what might be bugging you there? Okay, sure. So like, let's look at Q2-1, for example. So you've got 6 shapes, right? Like, don't even worry about the number inside. You've got 6 shapes. That's a pentagon, and then you've got a hexagon. 2, 3, 4, 5. No, this is actually a nonagon. This has 7 sides. Okay, I can't draw a 7-sided shape. This thing has 7 sides. Okay, so what's the probability that I choose this thing right here? So, right, exactly. And the probability that I choose this thing. Great. Okay, so you agree that they all have the same probability, right? They're all just 1/6. Okay, so maybe let me label these. I'm going to call this triangle 1, triangle 2, square 1, square 2, pentagon, and nonagon. Okay, nonagon has 7 sides. So what we want is the expected number of sides, right? So what I'm going to do is I'm going to define a random variable, and it's going to output the number of sides. So what is the output of T2? Like, how many sides does that triangle have? The second triangle. Perfect. Okay, and then how many sides does the pentagon have? Great. Okay, and now what is the expectation of a random variable? Right, there's some sort of formula. It's the sum over R of R times the probability that X is equal to R, right? Where R is the range of the outcome. So what is the range of this random variable? Like, what are all the possible outputs of this random variable? So we said 3 is a possible, 5 is a possible output. 5, 4, and 7, right? That's the output. Maybe let me put the 4 before the 5. Okay, so that's the range. So the expected four times the probability you chose a 4-sided thing, plus 5 times the probability you chose a 5-sided thing. Okay. Yep, no problem, no problem. No problem, everyone. Yeah. Thank you. Have a good night. I'll see you all on Thursday. Ciao.